next speaker is Professor Sandrine Peche. She got a PhD in 2003 from Swiss Fellow Institute of Technology in Lausanne, and she was an associate professor in University of Grenoble from 2003 to 2011, and she is now a professor in University Paris Diderot since 2011. And today she will talk about deformed ensembles of random matrices. So please.
Okay, so let me first thank the panel committee for the invitation to this congress, and I will speak about some deformations of random matrices. So let me start with a brief plan of the talk. So first I will define the model and what we call deformations of random matrices and the questions and motivations around these questions. So there will be two kinds of perturbations of random matrices, and they will be distinguished according to their rank. So the second part will deal with low rank perturbation, and the last one will be the extension to the full rank perturbation case. Okay, so deformations of random matrices are opposed to standard random matrices. So I will start with a few reminders about standard random matrices. So there are two kinds of usual random matrices. The first ones are the so-called Wigner matrices. So these are Hermitian random matrices with a big size M. So they are built from independent entries above the diagonal, which are either complex or real, and then we form a Hermitian or real symmetric matrix by symmetry. So the entries are assumed to be centered and with a finite variance, sigma squared, and it's now usual to rescale such a matrix by a factor 1 over square root over n. So the typical ensemble of Wigner matrices is so-called GUE, which is the complex Hermitian ensemble for which the entries are ID standard Gaussian entries and real along the diagonal. The other kind of standard random matrices are the sample covariance matrices. So this time we start with a rectangular matrix X of size n times p, with again independent entries which are all centered, independent, and admit a finite variance which we set equal to 1. Again, we consider the high dimension setting, so both dimensions n and p grow in a comparable way. P is a constant times n for e's. Starting from X, we then form the sample covariance matrix X star, and we divide by the factor n. This is a sample covariance matrix ensemble, and again, if X is Gaussian, we then obtain the standard Wishart ensemble of random matrices. So we can say that we are now at the point where the spectrum of such standard random matrices is quite well understood, and I will remind the main results in the next slide. So both ensembles yield Hermitian matrices with real spectrum, and I will call lambda 1 to lambda n the ordered eigenvalues of Hn. In the rest of the talk, I will mainly focus on complex Hermitian Wigner random matrices. Okay. So the first fundamental result of random matrix theory goes back to Wigner in the 50s, who has proved the following result. The empirical eigenvalue distribution of standard Wigner matrices converges weakly to the semicircle distribution whose density is given here. And this is the first universality result in random matrix theory. We don't need any assumption on the detail of the distributions of the entries Hij to state such a result. So this deals with the global behavior of the spectrum, and we can also consider more local questions by focusing on some more local properties, such as the behavior of largest eigenvalues. So, from a historical point of view, the behavior of largest eigenvalues has first been computed by Tracy and Widom for Gaussian ensembles of random matrices. This is in some way the simplest ensemble because the joint eigenvalue density can be computed. And then there has been more recently big amount of work established by two teams. On the one side, Dao Wenwu and Elvis Schlein-Yao and others on the other side, to extend the result to a much wider class of random matrices ensembles than the Gaussians. So the result is as follows. For a standard Wigner matrix, the largest eigenvalue converge to 2 sigma, which is the top edge of the support of the semicircle distribution. They fluctuate in the scale n-2/3, and the limiting distribution is called the Tracy-Widom distribution. So here you have a plot of the density of the largest eigenvalue here. And the leftmost curve is the distribution for the complex one. So let me say just one thing. So the Tracy-Widom distribution differs in the real and complex case. However, it's a much more universal object than the semicircle distribution. If we had considered sample covariance matrices, we would find another limit than the semicircle distribution, which would be the Marchenko-Bastow distribution. However, it's still true that the largest eigenvalue fluctuate with Tracy-Widom distribution in the large size limit. Okay, so Tracy-Widom is a very universal limiting object. So I now turn to deformations of random matrices. So the list is non-exhaustive, but I will be interested in 2 kinds of deformations. So let me start with the additive deformation. In the Wigner case, we start with standard Wigner matrix, and we simply add a deformation matrix A, which is a deterministic Hermitian matrix. We can do the same for sample covariance matrices by simply translating the rectangular matrix X with a matrix A, and then forms a sample covariance matrix. More interestingly, we can consider multiplicative deformation. So for this, we consider a matrix sigma, which is the population covariance actually, and which is a deformation of the identity matrix here. And we then form this new sample covariance matrix by multiplying both left and right by sigma to the 1/2. And the question is now, what is the impact of A on the asymptotic spectral properties of this new matrix Mn, which is a deformed one with respect to the standard ensembles. So let me give a few motivations for these questions. So first, there is a simple question, which is what can we say about the spectrum of the sum of 2 matrices if one knows the spectrum of each? And the first time this question was considered goes back to Thomas and Furedi in the 80s, who were actually interested in the adjacency matrix of the Aug19Tue random graph. This matrix is actually a matrix with Bernoulli entry, so This is actually a Wigner matrix with non-centered entries. So if we want to write it as a deformed random matrix ensemble, we simply consider a non-cascade Wigner matrix, and we simply add the deformation, which is m times j. J has all its entries equal to 1. And what they have proved is the following. Essentially, all the eigenvalues are smaller than 2 sigma square root of n plus lower order terms. So if we divide by 1 over square root of n, this is the usual behavior of eigenvalues of Wigner random matrices. There is only one eigenvalue which is actually enormous and which fluctuates around n times m. N times m is actually the only non-zero eigenvalue of this deformation matrix, and the fluctuations are Gaussian. Okay. A second motivation comes from mathematical statistics and questions in more applied domains. So instead of seeing A as deformation, we can see A as the signal, and the standard matrix is then the noise. And the question is, can we reconstruct the signal in the presence of noise? This is a question in statistics in high dimension, where one wonders what can be said on the population covariance if one knows the data, which is a sample covariance matrix. And this can be also of use in communication theory. So I give an example with cognitive radio. So this is an intelligent radio which tests a wide range of bandwidths to use unoccupied ones for transmission. So one has to be able to detect whether the bandwidth is used by a primary signal. So we can write a model for this. So x of n will be a time series of received signal which is high dimensional. And if there is only white noise, then the population covariance is just constant times the identity. So we are in the standard random matrix setting. If instead there is a primary signal, then the covariance is a deformation of the identity matrix. And we will see that it's possible to detect actually a signal in the presence of noise for such problems using random matrix theory. The last kind of motivations I want to discuss is from mathematical physics. So I will give a connection with directed population models. So we consider the lattice n squared, and at each site we attach random waiting times. All the waiting times are independent random variables. So I need to define the set of admissible paths which are paths consisting only of north and east steps. Given such a path, we can consider a passage time, say from the origin to some point mn, which is simply the sum of the waiting times you collect along the path. Okay, and we are then interested in the last passage time, which is the maximal such passage times you can get when you consider all the set of admissible paths from the origin to mn. So it happens that if one specifies a distribution of the waiting times, there exists a connection with random matrix theory. So I will give an example coming from Corwin and Benarous. So I will choose the waiting times to be essentially exponential random variables with rate 1. except on the first column and on the first row where the rates are simply distinguished. Okay. And so in a recent result by Bellows and Cohen, they have actually given the complete characterizations of the fluctuations of G of Mn as n goes to infinity, actually for any value of the slope m over n. But I will only discuss the case where it's equal to 1. And I don't want to really discuss actually the limiting distribution. All I want to say is for any value of the rate of the exponential, actually the fluctuation of G is related to the fluctuation of the largest eigenvalue of a random matrix, of a deformed random matrix. So this is, for example, the Tracy-Williams distribution. So there is a deep reason for that, which comes from an exact connection actually established by Hansen, which for a simpler model. So arrays in the directed population model the first column. So that the rate of exponential is only distinguished on the first row. Then Johansen has shown by direct computation in both ensembles then that G has then the same distribution of the largest eigenvalue of a sample covariance matrix, which is a Richard matrix. So this means that X has only complex Gaussian entries, and the population covariance is a rank 1 modification of the identity matrix. Okay, so this is the largest eigenvalue of a default random matrix ensemble, and Bellows and Cohen's result is simply a competition between two such simpler models, because either in the directed population model you first make a right step or an up step, and then we fall in Johansen's model. Okay. There also exists a connection with TASAP discussed by Alexei Bordin yesterday with some precise initial condition, and deformed random matrix ensemble may be of interest because they provide a family of limiting distributions for the different regimes of fluctuations in the KPZ universality class in dimension 1. So this is the possible applications for mathematical physics. Okay. I will now turn to the statement of a few results for the low-rank perturbation case of random matrices. So we consider an integer k, which is much smaller than n, and we consider a rank k deformation matrix A. So I need to define the eigenvalues of A, which are theta 1 to theta k. They are non-zero real numbers. I need a Hermitian matrix here. And the set of associated eigenvectors too. In the following, I will also need to define the multiplicity of each eigenvalue that will play a role in the rest of the talk. So that will be denoted by mi. So regarding the question about the impact of A on the asymptotic spectral properties of such a matrix, we can first answer from a global point of view. Essentially, nothing happens since both Mn and the standard matrix Hn have the same limiting empirical eigenvalue distribution, which is a semicircle distribution. This essentially follows from the interlacing property of eigenvalues due to Weil, for example. Okay. But for the behavior at the edges of the spectrum, the picture is quite different. So before I state the result, I need to say that I will only consider the largest eigenvalues, but the same is true for the smallest. Okay, so actually there is a phase transition for the behavior of largest eigenvalues. I will need some assumptions. Actually, I will need that all the entries admit a finite force moment, and then the BBP transition is as follows. So assume first that A has no eigenvalue greater than sigma. Then we don't see anything for the behavior of largest eigenvalues. They still converge to 2 sigma, which is the top edge of the support of the semicircle distribution. But as soon as A has one eigenvalue greater than this threshold sigma, then the largest eigenvalue will separate from the rest of the spectrum, and it will converge to some value which is rho theta I here, which is greater than sigma. Okay, so actually the result is much more precise than that, because to each eigenvalue theta I of A, which is greater than sigma, which we call a spike, there corresponds exactly mi, the multiplicity of theta I, eigenvalues of Mn, which separate and converge to rho theta I. Okay, this is some kind of exact separation phenomenon of eigenvalues. And I will call outliers those eigenvalues separating from the rest of the spectrum. Another remark first is that the phenomenon identified by Cognos and Freddy actually extends to the whole interval sigma to infinity. Cognos and Freddy's result was proved for the interval n square root of n plus infinity. Okay, but the interval is much more large actually. So this result is especially interesting for application, say, to mathematical statistics, because this essentially means that we are able to detect a signal if the signal is strong enough, if the size of the perturbation is strong enough, by simply looking at the largest eigenvalues. Okay, but in order to build a statistical test, we need some fluctuation, and this is the object of this new slide, where actually the BBP phase transition also arises at the level of fluctuations. So again, there are some moment assumptions on the entries that are to be satisfied. So typically, either the entries, the tail of the distribution of the entries have to exhibit some sub-exponential decay, or we will only need a finite force moment. Actually, this second assumption is believed to be the good one for any result. Okay, so the result is as follows. First, we consider the case where theta 1 is smaller than sigma, so that the largest eigenvalues do not separate. And in this case, even at the level of fluctuations, nothing happens. We are still in the regime of universality, though the eigenvalues fluctuate in the scale n-2/3 around 2 sigma, and the limiting distribution is the Tracy-Widom distribution. This is exactly the same as for standard Wigner matrices. So this means that when the signal is not strong enough, we cannot see anything, even the level of fluctuations. When theta 1 is greater than sigma, then the situation is completely different actually. So first, the M1 largest eigenvalue converge towards theta 1, fluctuate in a new scale 1 over square root of n, and the limiting distribution is that of the eigenvalues of a small random matrix V. So initially the BBB phase transition was proved for the deformed GUE in the case where H is Gaussian. In this case, V would be Gaussian, a GUE actually. But in the general case, V is neither Gaussian, neither universal. It might be strongly non-universal. So this is a really new regime in random matrix theory where we obtain non-universal asymptotic results. And last, the transitional regime where theta 1 is equal to sigma, then again the largest eigenvalues converge to 2 sigma, fluctuate in the scale n minus 2/3, and simply the limiting distribution is not the Tracy-Widom one, but a modification of this distribution, depending on the multiplicity of theta 1, actually. Okay, so let me briefly give some ideas of the proof. So first, for the initial results for the deformed GUE. So the deformed GUE is probably the simplest ensemble of deformed ensemble because there are two miracles. The first one is that we are able to compute the joint eigenvalue density for the deformed GUE. This follows from some algebraic identities, and using this joint eigenvalue density, we are able to compute in an explicit way, say, statistics of eigenvalues. We are able to compute their expected values. So especially we are interested in such local eigenvalue statistics, which can be then used to compute the distribution of largest eigenvalues. Okay, so we consider a symmetric function f of, and we consider the expected value of this functional of m unordered eigenvalues. It happens, this is the second miracle for the deformed GUE, that this quite complicated functional is actually given by a simple integral of f with respect to the determinant of some matrix. This matrix again is rather simple since the entries can be expressed in terms of what is called a correlation kernel. I don't want to insist on the form of this kernel. What is important is that it's given by a double integral in the complex plane, and it only depends on the deformation matrix A through its empirical eigenvalue distribution. The yi here are simply the eigenvalues of A repeated with multiplicity. This follows from the rotational invariance of the GUE. So we are then able to perform the asymptotic analysis of this correlation kernel and then to compute the limiting distribution of the largest eigenvalues. The next part of the job, which has been accomplished by many authors and especially Antinomes and Yin, was to extend the result for Gaussian ensembles to non-Gaussian random matrices. And this has been accomplished using a very precise knowledge of the resultant of standard random matrices. So typically, when one is far enough from the real axis so that the imaginary part of Z is much greater than 1 over n, the resultant of a standard Wigner matrix behaves in some way like a diagonal matrix, whose diagonal entries are almost constant and depending on the semicircle distribution. Using this quite precise estimate, one can then show that when θ1 is smaller than sigma, so that eigenvalues do not separate, the largest eigenvalues of Mn stick to those of the non-deformed matrix. Let me now turn to some rough explanation of the spike case and explain why the matrix V may be non-universal. So first, by simple algebra, it's possible to show that lambda is an outlier, so that which is an eigenvalue of Mn, which is typically not that of Hn because it's outside the support of the semicircle distribution, if and only if this equation is satisfied. This equation actually involves only k by k matrices, so small matrices. We are no longer, typically if k is fixed, in the high dimension setting. Using the fact that the resolvent is in some way some diagonal matrix with almost universal limit, it's not so difficult to believe that if one considers the case where θ1 is greater than sigma as associated eigenvectors which are delocalized, so that uniformly spread among the n-canonical vector bases, then this equation becomes some kind of averaging of the resolvent entries, and roughly speaking, we can believe that in this case V will indeed be universal, and this is indeed the case because V will be the sum of a Gaussian matrix and a deterministic matrix, which essentially depends on some kind of third moment of the entries. On the other side, if eigenvectors associated to θ1 are localized, then we may focus on the fluctuations of one entry of the resolvent, and I will only give the worst case. This has been considered by Capitaine, Donetti, Martin, and Ferral first. So this is the case where k is equal to 1, and so there was just 1 non-zero eigenvalue, and the associated eigenvector is the first canonical vector basis. In this case, one can show that V will be the sum of a Gaussian and an independent random variable which has the same distribution as H11. So this result is a strong non-universality result, because the limiting distribution strongly depends on the distribution of the entries here. Okay, so I will now turn to the extension to the full rank perturbation case. So this time we consider the case where the empirical eigenvalue distribution of A converges to some probability distribution mu, and no longer the delta, the Dirac delta mass at 0. So first, the picture is different even from a global point of view. Obviously, the limiting spectral measure of A plus Hn will not be the semicircle distribution. And Pastor and Basil Schuck have considered this question. So they have actually characterized the limiting empirical eigenvalue distribution of A plus Hn. So this will be a probability distribution mu. This probability mu is actually characterized by its Stitcher's transform, whose definition is given here. This is Stitcher's transform of a probability distribution mu, and actually they characterize mu through a fixed point equation for this Stitcher's transform. Okay, so starting with this definition, in general, it's very difficult to have a clear picture of what mu is. So we know that it admits a density. This is a result of Bian. It may have non-connected support, so different connected components. It is the new feature from the low-rank perturbation case, and in general we cannot compute the density. So the question is now, does the same phenomenon appears in the full-rank case? So this question has been answered actually by Capitaine Donatille Martin, Ferral and Février in the recent years. So they have been able to give a necessary and sufficient condition so that there are outliers. So again, we need the entries to admit a finite force moment, but they are able to give this necessary and sufficient conditions so that an eigenvalue of A theta I is a spike. Okay? They are also able to compute then the location of the associated outlier, but I have not written it because it's quite a technical formula. Okay. So the next question is, are we then able to compute the limiting distribution of such outliers, or if there are no outliers, of the largest eigenvalues or eigenvalues at the edges of the spectrum? And this is some recent work with Mireille Capitaine, and this has also been considered by Tatiana Sherbina before. So we are only able to give an answer for the simplest ensemble of deformed matrix ensemble so far, which is the deformed GUE. Again, this follows from the same reason as before. In this case, we are able to compute all the eigenvalue statistics. And the result we obtain is as follows. So when there is an outlier, the limiting fluctuations will be those of the eigenvalues of a Gaussian matrix. So this will be a GUE type of fluctuations. At an edge of a connected component of the support, we will obtain Tracy-Widom fluctuation with the usual n-2/3 scale. However, for the Tracy-Widom distribution to be true, we need this condition. This is a necessary condition. If this condition is not true, then we obtain at the edge of the spectrum Gaussian fluctuations. And the reason is that this condition is not true when the density nu vanishes too fast, actually. So there are some new phenomena in the deformed GUE in the full-rank perturbation case, and so far there does not exist any extension to other ensembles of non-Gaussian random matrices. So I didn't speak about sample covariance matrices, but I would just like to say that for sample covariance matrices, both in the low and full-rank case, we have a much better understanding of asymptotic behavior of the largest eigenvalues. Actually, we know, this is a result of Baiyao, that we know the condition so that there are outliers. We know that the outliers fluctuate in the scale n-1/2, and the fluctuations are necessarily those of the eigenvalues of the Gaussian matrix. And also we know that when there are no outliers, the largest eigenvalues will exhibit necessarily Tracy-Widom fluctuations. Okay, so the reason why it's more simple for sample covariance matrices in that there is more averaging in the entries of a sample covariance matrix. One entry is already an average over ID random variables. Okay, so as a conclusion, I would like to speak about a few things I didn't address in this talk. So first, the behavior of eigenvectors, because this is important for the problem of reconstruction of a signal. It happened that we also know a lot of things now about eigenvectors of standard and deformed random matrices. And in particular, when there is an outlier, eigenvectors exhibit some localization, which is not true for standard Wigner random matrix. Another question which is of interest, one can see the Tracy-Widom distribution as some kinds of statistics of extremes, because it's a distribution of the largest eigenvalue. So it would be natural, actually, to expect a transition from usual statistics of extremes to the Tracy-Widom distribution. We can simply consider a diagonal matrix with ID entries and add a Wigner matrix by suitably choosing the weights of either the diagonal matrix or the Wigner matrix. We could expect a transition from Weibull or Gumbel distribution to Tracy-Widom. So these questions have been considered by Lee and Schnelli and also Johansson, and interestingly we are able to see a transition from Weibull to Gaussian, which plays a role actually of Tracy-Widom, but not for the Gumbel distribution. So far we don't really understand this fact. Another question about local eigenvalue statistics, which is of interest in random matrix theory, is to consider spacing between nearest neighbor eigenvalues in the bulk, this time of the spectrum. So for standard Wigner random matrices, the usual spacing is of order of 1/n, and it is asymptotically determined by the well-known sign kernel. It happened that for the bulk of the spectrum, the deformation has no impact. This is a result of Aug and Wu. This is the same for deformed and non-deformed ensembles. So deformation only impacts actually the edges of the spectrum for both additive and multiplicative deformations. And last, I addressed only deformations of Hermitian random matrices, but now it's also of interest to look at deformations of non-Hermitian random matrices. And this has been considered recently by Thierry Tao and also Florent Benet-Georges and Jean Roger. I thank you for your attention.
Any question or comment?
So correlation kernel for deformed GUE. So whose result is that?
Whose result?
The formula for the double integral formula of the kernel.
This goes back to Johansson, the first study of the deformed GUE.
Any other question?
Is there some good result for the deformed?
No, we can only consider the complex case because actually this computation comes from the Alexandra-Dixon-Zuber integral over the unitary group. So we have nothing in the real case.
So if there is no further question, then let's thank our speaker.